Hello. First of all, I would like to thank the organizer for the nice opportunity to give a talk. Today I present the results obtained jointly with Evgeny Apushkinsky and Vadim Kozhevnikov. Both are from the Petrograd St. Petersburg Polytechnic University. We study a nonlinear hyperbolic equation arising in modeling the dynamics of vortic displacement in superconductors subjected to magnetic fields, both constant and alternating. Configuration of magnetic fields is shown here. They are orthogonal each other. In our experiment, the frequency of an alternating field was 30.7 MHz, which corresponds to the dimension of the superconductor material grains that lies in the range between 20 till 50 micrometers. The amplitude of the alternating field was much smaller than the magnitude of the constant one, and this was subjected to the pulse temporal modulation. The magnitude of the alternating field reached nearly 5 Tesla. All the experiments were conducted at the temperature below superconducting transition. A grain of the superconducting sample with a constant magnetic field that has penetrated in the form of fluxoids is shown in the left figure. The red dots correspond to pinning sites which rise at defects in the crystal lattice. The alternating magnetic field acts on the vortices on the surface of the superconducting sample, causing these vortices to oscillate. This oscillation penetrates deep into the grain and sends the pinning centers in motion, which transmit acoustic vibration throughout the crystal. On the right figure, we see the mechanical model. Here, the black balls correspond to the oscillation nodes of the crystal lattices, and the connection between the balls correspond to vortices, along which a fluxoid wave, an analog of a band tornado, propagates. This oscillation between the balls exhibit very low damping compared to the damping of the spring crystal lattice oscillation. On this slide, we see the dynamics of the mechanical models. Excited by a pulse from the left end, the system, due to the elasticity of the vortices, causes the spring throughout the model to oscillate. The oscillation of the spring dump out quickly, while the oscillation of the string deep inside the conductor, where there is no radiation and consequently no losses, persist. This string oscillation form different waves. We will study these waves. The first equation describes the motion of vortex displacements in an elementary volume in the absence of jumps and accounting for all forces acting on the fluxoid, and after normalizing the vortex displacement. We have boundary conditions, and initial condition is defined as follows. We linearize the first equation by expanding the exponential function into power series in y and retaining only the first order terms and add the driving force. This is correct if the driving force acts over a short time during which nonlinear effects have not yet manifested. As a result, we get an inhomogeneous linear equation, which we solve in the moment when the external force ceases. Thus, we take an initial data. The first equation on the slide is a nonlinear equation that admits the existence of traveling waves. In this class, the unknown function depends on the coordinate and time not separately but through the combination x minus bt, where b represents the wave speed. Introducing the new variable z and a new function g of z, we transform our nonlinear equation into the following form. Note that in this form, changing the sign of g to its opposite does not alter the form of the equation. We simplified this equation by expanding the exponential function in a power series in g around 0, assume that g is non-negative, and proceed to sequential analysis, retaining progressively higher order terms in the expansion. We begin with linear case. It is known that solution has the following form, which correspond as standing waves, which forms within the fluxoid. The analytical expression for the standing wave, along with the dispersion relation, from this we obtain the value of the group velocity, which is equal cf square over the b. Here we consider the equation with quadratic nonlinearity. It is known that this equation has a partial solution. If B is bigger than CF, then solution is unstable, so in this case it's not very interesting. Otherwise, if B is smaller than CF, we have a soliton solution. This solution is stable, and it should be noted that a soliton approaching a pinning center can either reflect from it or pass through a node-cyst. The latter is possible, for example, if the pinning center is oscillating and its amplitude equals the amplitude of the approaching fluxoid soliton. Complete reflection of the soliton will occur when the pinning centers are at rest. A numerical analysis of the nonlinear equation with quadratic nonlinearity indicates that the unique soliton solution exists and at amplitude g is equal 3. We retain all term in the expansion of the exponential function in the equation up to the cubic 1 and get the following equation, now with cubic nonlinearity. Analysis of the restoring forces gives the following result. On figure 4, we see the graphs of all restoring force we considered. The graph indicates that at least up to a relative displacement of 3, the restoring force will be greater when accounting for cubic nonlinearity than if we accounting only for up to quadratic nonlinearity. In other words, adding a cubic term to a quadratic one does not move the problem further from the linear, but on to contrary, bring it closer. This suggests the existence of periodic solutions in the problem with cubic nonlinearity that are similar to those in the linear case. To find periodic solution, we transform this equation into the following form, and this equation defines the trajectory of the relative fluxoid's displacement in the phase plane. Equation with cubic nonlinearity may have a solution in form of a periodic function. Here, periodicity in amplitude and phase is in principle possible. For further investigation for such an equation, it's natural to apply the method of slowly varying amplitudes. And according to this method, we see that the solution of the equation has the form which is presented here. The phase of the oscillation depends on the square of the amplitude. A restoring force with cubic nonlinearity is active, and if a standing wave regime is realized, the resulting anharmonicity makes it possible to observe an echo in an ensemble of such anharmonic oscillators. Based on numerical study of phase shift of the equation, the following main conclusion can be drawn. For the small amplitude, phase is close to 0 grade. For moderate amplitude, phase gradually increasing. And for the large amplitude, abrupt phase changes becomes possible. Critical amplitude for 180 grade phase shift lie in the range between 1.1 and 1.3. Summarizing the above results, we can conclude that the analytics based on the equation we proposed allows us to expect the existence of nonlinear waves and particularly solitons. Here you can see the references that we use. And the last, thank you very much for your attention.